All right, continuing on. We kind of already did this before, but I'm just putting it in here again. So when an integral is improper, it has a finite interval of integration. It is improper because its interval spans on an infinite discontinuity or vertical asymptote. They're harder to spot, so you do have to be vigilant. Okay, so basically, looking at this problem, it actually looks like a proper integral. It doesn't really fit the idea of improper that we've been talking about. But what you notice is it is, well, actually, let's do this one on the calculator because that's what we're supposed to do with this one. So if you plug this in, you will get 1.430 on your calculator. Plug this in and you get 1.485 on your calculator. Plug this in, you get 1.497. So really, the integral, all right, from 0 to 1 is actually converging to 1.5. So try this one, you get 4999.5. You try this one, you get 499999.5. You do this one, you get 49999999.5. So obviously, it is not converging to any finite number. Sorry, and this should have been 1.497. Okay, so this is diverging. So we've kind of already looked at this before. Okay, we approximated the value of integrals using a calculator so that we can see what it is that we're talking about. Now, when we recognize an infinite discontinuity at an endpoint, we have to set up one-sided limit. So if you notice that one of these endpoints is going to be an infinite discontinuity, then we have to set up a one-sided limit. When the infinite discontinuity is on the interior, though, we have to set up two integrals. So this is what's hard to spot. One approaching the vertical asymptote from each side. So here's the idea. Let me grab my calculator. Alright, so if you look at the graph of this function right here, it kind of looks a little something like this. I'm just going to draw it off to the side. Okay, it kind of starts off at negative infinity and it kind of tapers down and then it picks up again up here and it goes off to positive infinity. But what's happening here is that this is telling us that we want to find the area of this function from 0 to 1. Now what do you notice is happening at 0? So at 0, there's a vertical asymptote, so we can't really use that point. So it's undefined at x equals 0. So when we set up our limit as a or b, whatever you want to call it, approaches 0, we want to specify where are we approaching 0 from. Now since this is from 0 to 1, we want to find the area here. We want to approach, so our graph is actually getting closer to 0 from the right. And then you set this up from a to 1 because that is making it improper, of x to the negative 1/3. The reason why we write it like this is because it's easier to find the integral. So then this becomes the limit as a approaches 0 from the right of 3, so 3/2 x to the 2/3. Okay, add 1 and divide it by that thing. Add 1 gives us 2/3. Divided by 2/3 is the same thing as multiplying by 3/2 from 1 to a. See, I'm not using the limit yet until I have finished my integral portion. So now we're going to plug in the 1 and then minus the a. And you notice that 3/2, 1 to the 2/3 is 1, times 3/2 is just going to be 3/2. And then the second part, of course, we're going to have to plug in our a to the 2/3. Now I can plug in my limit, and my limit is approaching 0 from the right. So here, as I approach, as a gets closer and closer to 0, what is happening to the 2/3? Okay, I'll give you guys a minute to kind of think about this, because this is just like saying that this is the cube root of a squared. So plug in a very, very small number and do this, and you see that it's 0. So this is just going to be 3/2 minus 0, which is 3/2. So the area of that section is 3/2. Alright, looking at this function, where is it undefined? If you plugged in 0 over here, what would you do? So it's undefined at x equals 0, so of course we're going to have to figure out where we're approaching 0 from, and since it's from, it's going to 1, we're going to be approaching 0 from the right of x to the negative 3rd. And I'll let you guys figure this one out. And I'm just going to let you know that the answer is diverges. So it's not a convergent function. Alright, next up, what is going on here? Why is this improper? So the reason it's improper is because this function is undefined at x equals 27 at one of the endpoints. So we're going to have to treat this like an improper integral and use the definition as the limit of a or b, whatever letter you want to use, approaches 27, but here we're going to be actually approaching 27 from the left, of 0 to a. This is our improper portion of dx over the cube root of 27 minus x. And next part is integrate. So you integrate this using u sub. Let the bottom be 27 minus x, so that du can just be negative dx. Okay, I'm not going to show that part, but you guys need to make sure that you're figuring this out. So when we integrate, we end up with negative 2/3, 27 minus x to the 2/3 from a, we're using a this time, to 0. Now plug in your a and your 0. So if you plugged in your a, you would get negative 2/3. We're still with the limit. We haven't really used that yet. So negative 2/3, 27 minus a to the 2/3 minus, so here if you plug in 0, you get negative 2/3 27 to the 2/3, which actually is just going to be 9. Okay, and I'll let you guys finish this off. And you should get 27/2. All right, what if there is both an infinite bound and a discontinuity? So here, you notice that it's undefined at x equals 0, but we also have an infinite bound. So you just have to split it up into two separate parts and use some value c in between. I would like to do this one together in class as a bell work, so we'll leave that for tomorrow. Okay. So this is the last part of improper integrals. Sometimes we cannot find the antiderivative of an integrand, of an improper integral. However, we might be able to draw a conclusion about its convergence or divergence. So we can't really integrate, but we can draw a conclusion. So if we can compare it to something similar to which we already knew. So this is called the direct comparison test for conversion and diversion, aka DCT, direct comparison test for convergence and divergence. Okay, so if you look at the examples that we have, these are pretty hard examples to integrate. Okay, they're pretty hard examples to integrate. So if I can't integrate e to the negative x squared, then maybe I can compare it to something that I do know, which is e to the negative x. Alright, so let f and g be continuous on the interval from a to infinity. And then basically you're going to plug in f and g, two parts, and say that they are going to be greater than 0. So it'll make more sense once we do this. And basically, if that thing that you're comparing, if it converges, then the other function that you are figuring out also converges. So in other words, if the larger one converges, the smaller one will converge. And then if the smaller one diverges, then the larger one also diverges. Okay? So if the smaller one diverges, the larger one diverges. Here, if the smaller one converges, then the larger one will also converge. So the smaller one or the larger one, depending on what you're looking at, will kind of determine what we're doing. So just to draw a quick little graph, I'm going to do this on the back side. Here's the idea. If you have two functions, let's call this one g of x, and this one, let's call it f of x. So this guy right here is the larger function. Okay? Just because if I had to compare, let's call this one e, and this one's going to be e squared. So basically, if this converges, then guess what? This comparison graph will also converge. So you have to find a function that looks similar to what it is that you're talking about. So I'm not really going to get too far into this in these notes, but here's the idea. So if e to the negative x squared is greater than or equal to 0, and e to the negative x is greater than that, so that means that this guy right here is the larger one. For all functions x greater than 1, determine if the integral from 1 to infinity of e to the negative x squared converges or diverges. So here the idea is that the larger one needs to converge for the smaller one to also converge. If this one diverges, then this one diverges. So since I can't integrate, or I don't know how to integrate this, I'm basically going to focus all of my attention on this function right here. So this is what is hard. It's basically figuring out a function similar that you know how to integrate, similar to what it is that we're talking about. So the function that I'm going to focus on is e to the negative x. And we know that we can use the limit of improper integrals of 1 to b, e to the negative x dx. And we know that the integral of e to the negative x is just negative e to the negative x. So it's just negative e to the negative x from b to 1. Now I can just plug in my b to 1. So this becomes negative e to the negative b minus negative e to the negative 1. So let's clean this up before we plug in our infinity. So this is negative 1 over e to the b plus 1 over e. And now I can plug in my infinity. So this is negative 1 over e to the infinity plus 1 over e, which is just some number. Who cares what it is? Well, actually we do care what it is in this case. So in here, negative 1 over e to the infinity. E to the infinity is a really big number, so that means negative 1 over e to the infinity is actually going to be 0, and therefore 0 plus 1 over e is just 1 over e. So since this guy, the larger one, converges, since we converge, so because e to the negative x converges, therefore e to the negative x squared also converges by using dct. Okay, so I'm just going to give you an example here, because here they gave us what to compare. Alright, so in this case, we can compare a couple different types of functions. And it depends on which one you choose. So we can, possible comparisons. Alright, that 2 really doesn't mean anything. It's just going to be adding 2. So we can do cosine of x over x. But that's still hard. We can also do 1 over x, or we can do 2 over x. So these are 3 possible comparisons. You notice that the key is the denominator. The denominator kind of tells us almost everything that we need to know. So just to be on the safe side, I'm going to pick the easiest one, because I know the integral of this pretty easy. So we're going to compare. We're going to say that 1 over x is greater than or equal to 0. And then this guy, is he bigger than or smaller than the 1 over x, he's obviously going to be bigger. So here the question is, this is smaller, right, than our original. So here the smaller one needs to diverge. And if the smaller one diverges, then we can assume that this one diverges. Now if the smaller one converges, then we can't use DCT. Do you get what I'm saying compared to the definition up here? Okay, and I think I said it wrong in the beginning. I apologize. Alright, so I'll leave you with this, and you determine if it diverges or converges. Alright, we're done for now.